Acoustics in CLT buildings. Noise pollution is a disturbing noise with a harmful impact on human or animal life. Worldwide, the source of outdoor noise is mainly caused by machines and transportation systems, for example, cars, lorries, trains, etc. However, indoor pollution is created by human noises, banging, radios, loudspeakers, home appliances, and other daily activities. Just to underline this point, 70% of workers believe they could be more productive in a less noisy office environment. Here we have a graph that shows the noise effects, starting from the short-term symptoms, such as a decrease in quality of sleep, an increase in irritation, stress, and distraction, and sound distortion. The chronic effects can be hypertension, reduced learning and productivity, and endocrine disruption. Finally, you can see a list of the risks due to prolonged exposure over time. Let's start with some basic acoustic concepts. When a body starts vibrating, the particles in contact with it begin to oscillate, setting in motion the adjacent ones and generating a perturbation in the propagation medium, which spreads to the surrounding environment. This vibration can generate a sound wave that spreads through air, gas, liquid or solids. Its speed and propagation depends on the physical properties of the medium. We can consider wood as a straw model. It shows the shape of the timber fibers through which the structure gets its lightness and rigidity. Just to give you an example, sound can move up to 3 times faster in the longitudinal direction of the fiber than the transversal one. Here are some definitions to understand the basic acoustic concepts better. When you describe the sound wave, you need the following physical measurements. Speed, c, expressed in meters per second, depends on the physical properties of the body in which the wave spreads. Frequency, f, measured in hertz, quantifies the number of complete oscillations in 1 second. Period, t, expressed in seconds, is the inverse of frequency and describes the time required to perform a complete oscillation. Wavelength, lambda, measured in meters, quantifies the distance covered by the sound wave in a period. Amplitude, A, expressed in meters, indicates the maximum magnitude of the oscillation. Frequency, wavelength and speed are linked by the following mathematical equation. Lambda is equal to the ratio of speed and frequency, and this is equivalent to multiplying the speed and the period. So, the lower the frequency, the lower the pitch of sound, which is similar to a drum. Conversely, the higher the frequency, the higher the pitch of sound, which is similar to a violin. You will now listen to 2 different audio tracks of a few seconds long. The first one represents a sound of 440 Hz, and the second one is a higher sound of 7040 Hz. In this graph, you can see some frequency ranges which show some common sounds in everyday life. For example, heels from shoes, dogs barking, children crying, etc. The pressure level of the sound is expressed through the decibel scale. The ear has the remarkable ability to handle an enormous range of sound levels. In order to express levels of sound meaningfully in numbers that are more manageable, a logarithmic scale is used, rather than a linear one. This scale is the decibel scale. 0 decibels is the quietest sound audible to a healthy human ear. From there, every increase of 3 decibels represents a doubling of acoustic power. The relative loudness that we perceive is a subjective psychological phenomenon, not something that can be objectively measured. Most of us perceive one sound to be twice as loud as another when they're about 10 decibels apart. For instance, a 60 decibel air conditioner will sound twice as loud as a 50 decibel fridge. Yet that 10 decibel difference represents a 10-fold increase in intensity. A 70 decibel dishwasher will sound about 4 times as loud as the 50 decibel fridge. But in terms of acoustic intensity, the sound it makes is 100 times as powerful. This audiogram contains a decibel scale and a frequency range in hertz, thus identifying the fields where the various sounds can be placed. Here you can see that the yellow area characterizes the sound coming from speaking. In this slide, we want to show you the perception scale for noise. For example, a sound around 90 decibels can be very annoying, while sounds that are between 30 and 40 decibels are less disturbing. Timber building and acoustics. The World Health Organization defines the concept of well-being as the state of complete physical, mental, and social well-being, and not merely the absence of disease or infirmity. Acoustics plays an important role in our well-being. So, over the years, the concept of treating acoustics in buildings has grown, and it is connected fundamentally to the person's psychophysical well-being. Think for a moment of an acoustically designed building, a building where quietness and concentration reigns, thus increasing the quality of life. For this reason, there is a field of acoustic studies known as building acoustics. It studies and optimizes the insulation of buildings. Specifically in construction, sound can be divided into 2 categories, depending on the method of transmission. One is called airborne excitation. Here, the source starts vibrating, and the particles in contact with it begin to oscillate, setting in motion the adjacent elements, for example, a wall, which radiates this energy into the receiving room. Then there is structure-borne excitation. This is generated by a mechanical impact, and the sound crosses the structure, carrying the vibrations from room to room, even when not directly adjacent. Like all light constructions, wooden structures don't have high acoustic performance at low frequencies. In fact, wood has always been used to make musical instruments, thanks to its ability to radiate sound. For this reason, you can apply the principle of disconnection. Disconnection is a construction technique or action which keeps elements isolated or separated from each other, where contact would otherwise allow the transmission of vibrations and consequently produce noise. Here, the construction technique is made up of a mass, spring material, and another mass. On the left is a diagram of the concept, and in the picture on the right you can see the mass, which is represented by CLT, and the spring material, which is the soundproofing profile. These soundproofing strips are defined as resilient materials. They have a function similar to shock absorbers in a car, so you have to choose them according to the load and the frequencies on which you want to isolate the structure. In our catalogues, there are linear load bands recommended according to the different stiffness of the resilient interlayers. Regulatory framework and flanking transmission. When you need to design a building, considering the acoustics, you should follow a design process that essentially consists of the following steps. Step 1 is an assessment of the outdoor noise. The assessment of the acoustic impact aims to quantify the level of noise present in the area, and also aims to verify that it complies with the national requirements. Step 2. The acoustic design must follow the standardized methods of EN ISO 12354. Step 3 is to monitor noise caused by temporary activities, for example, the acoustic impact of construction sites. Step 4 is the verification of passive acoustic requirements for buildings. These measured values must comply with specific legal acoustic requirements. And step 5 is to identify the acoustic classification of the building units. The standards used for the design phase is the EN ISO 12354. ISO stands for International Organization for Standardization, while EN stands for European Standard. This slide shows 3 different parts of the standard that must be respected in building acoustics. These parts are related to the acoustic behavior of some building elements. The legislation provides a method of calculation that starts from experimental or laboratory values. Then it incorporates them with factors that take into account the inclusion of elements calculated within a much more complex structure. Let's see an example. The acoustic performance of a partition tested in a laboratory is characterized only by the direct transmission, D, and is expressed by the sound reduction index, R, or transmission loss, TL. However, the acoustic performance of a partition measured in situ is characterized by the direct transmission, D, and the flanking transmission, L. In the slide, you can see 3 possible paths for flanking transmission. In this case, the acoustic performance measurement in situ is expressed by the apparent sound reduction index, R'. This is because in a real building, the effects of lateral transmission, also called flanking, have to be considered. Also, other indirect components need to be considered, such as the coatings or claddings, the heating systems, etc. So the calculation of the apparent sound reduction index, R', involves the analysis of the direct transmission through a partition and of the sound transmission through the side structures. Thanks to the norm EN ISO 12354, R' can be derived from numerical models. Focusing on the acoustic design phase, if you want to calculate the blue element, we need to consider all the neighbouring building elements in order to calculate the transmission loss and determine the components of the flanking transmission. Going on with the calculation model, here is the equation where you can see the different contributions in more detail. In particular, this equation shows the calculation of the sound reduction index Rij in relation to the generic transmission path from I to J. Under the equation, there are the definitions for all of the factors related to the equation. The important value for Rothoblaas and the project is the Kij from I to J. I will present this in the following slides. In order to have a correct evaluation of the flanking transmission, it's necessary to evaluate properly how the layers coating the walls and the hollow spaces intersect with each other. And here on the slide you have an example. The flanking transmission involves the outer layer of the side structure, which is in direct contact with the source and receiving rooms. So you need to understand how these various elements are connected and fastened. This is where the FLANKSOUND project can be applied. The FLANKSOUND project. This is the last chapter of the presentation, but the most interesting. So what is the FLANKSOUND project? The purpose of this project was to determine and define the flanking transmission paths for different connection systems used in CLT structures. This was done by using the measurement of the vibration reduction index Kij. This big project was run by Rothoblaas and the University of Bologna. 7 CLT manufacturers were involved, using a wide variety of L, T and X configurations, imitating a large number of junctions and realistic details. The aim was to test the influence of the different fastening systems on the flanking transmission and also the benefits of the soundproofing profiles. This was the first project in the world of its kind, focusing on the connections from timber to timber. Coming back to the calculation model, in this project we obtained the Kij in order to use it in the more complex equation that is used to get the sound reduction index R'. In the next 3 slides, there are some models of configurations assembled in Rothoblaas warehouse. In this first slide, you can see the T configuration. The dimensions of the panels were between 3.5 and 4 meters in width and approximately 2.5 meters high. In this second slide, you can see the X configuration with 4 panels. And finally, in the third slide, there is the X configuration with the addition of a slab over 1/4 of the configuration. The measurements were conducted by the University of Bologna, Italy, and conform to ISO 10848. The measurements were recorded by using a shaker, with pink noise filtered at 30 Hz for the vibration velocity difference, while an impulse response shaker with an ESS test signal was used to evaluate the structural reverberation time. Here in the slide, you can see the screws used to fix magnets, which held the accelerometers. In this small presentation, I'd like to show some results to give you an idea what you can find in our FLANKSOUND project. We shall start with the influence of the resilient interlayers with a wall-to-wall junction and a wall-to-floor junction. We will close with the different behavior of fastening systems in different dimensions, shapes and numbers. Let's start with the transmission of vibration in wall-to-wall junctions. In this slide, the product construction sealing was used as an airtight solution. This application respects the principle of disconnection, creating a mechanical breakdown that dampens part of the vibrations. We tested the configuration without construction sealing, as shown on the left, and with construction sealing, as shown on the right. Here, under the images, you can see the average values of Kij through the different paths. Let's take the path from points 1 to 3 as an example. On the right, the Kij, the vibrations reduction index, is about 4 decibels higher than in the configuration without construction sealing on the left. The next comparison concerns the benefit of the resilient interlayers xylophone, used to reduce the sound vibrations between structural elements. We measured the experimental Kij in order that we could compare them with the ones given by EN ISO 12354. On the left, you can see a picture showing the configuration of CLT elements in wall-to-floor junctions. On the right, you can see the same image but with the resilient interlayer xylophone used to disconnect the CLT elements. Under these images, there's a description of the composition of the junction. HBS partially threaded screws with a diameter of 8 mm, a length of 240 mm, and a step of 300 mm. A TTN angle bracket with a width of 240 mm and a step of 800 mm. And a WHT 440 hold down. In this next slide, under the images, you can see the average values of Kij throughout the different paths. Let's take path 1 to 3 as an example. On the right, the Kij, the vibrations reduction index, is about 3 decibels higher than in the configuration without xylophone on the left. The last example refers to the different types of screws. In particular, we analysed the behaviour between the partially threaded and the fully threaded screws, considering the various characteristics of each type. Here in the slide are 2 typical configurations of wall-to-wall junctions. On the left, HBS partially threaded screws are used, with a diameter of 8 mm, a length of 240 mm, and a step of 200 mm. On the right, VGZ fully threaded screws are used, with a diameter of 9 meters, a length of 400 mm, and a step of 300 mm. In this next slide, under the images, you can see the average values of Kij through the path. Here on the left, the Kij, the vibrations reduction index, of the HBS junction is about 7 decibels lower than in the configuration on the right with the VGZ junction. This is possible because of the different pressure created between the 2 surfaces of the wood elements using different fastening systems. Stay tuned. If you're interested in discovering more information related to this topic, please go to these following links. And finally, the following titles are papers that Rothoblaas has published in cooperation with the University of Bologna. Rothoblaas thanks you for your attention.